Whenever we add heat energy or remove heat energy from a substance, we might expect it to change temperature. So when Q is positive, we're adding heat energy. So we might expect the temperature to rise. If heat energy is removed from this substance, so for example, if we have a negative Q, where heat energy is coming out of the substance, we might expect the temperature to fall. And this isn't an unreasonable assumption. In fact, in the last lesson, we learnt that every unique substance has its own specific heat capacity. And the equation for specific heat is the specific heat is equal to the net energy going into or coming out of the substance divided by its mass multiplied by its change in temperature. In other words, the heat capacity is the energy required to change the temperature of 1 kilogram of substance by 1 degree Celsius or 1 Kelvin. Now, it doesn't matter whether we use Celsius, degrees Celsius, or Kelvin here, because we're looking at a change in temperature. We're not looking at the absolute temperature, we're looking at a difference in temperature from the final temperature minus the initial temperature. So the change in temperature is equal to the final temperature minus the initial temperature. And a difference in 1 Kelvin and a difference in 1 degree Celsius is the same thing. And to find out the change in temperature from this substance, when we add or remove energy, we can rearrange this equation. And the specific heat capacity can only be found experimentally for each substance, and it's different for each substance. So ice water will have a different heat capacity than liquid water, for example. And solid lead will have a different heat capacity to solid iron, for example. Every substance has its own unique heat capacity, even down to the state of the substance. And what I mean by this is we could have a substance in a liquid state, we could have it in a solid state or a gaseous state. And each of these states will have its own unique specific heat capacity. So with this equation here, or with this equation, we can make predictions on how much an object would raise or lower its temperature with a change of net heat energy. And in fact, if we plot the temperature change as a function of heat energy, Q, we would get a linear graph. And this is a plot of temperature change as a function of heat energy. And let's say that this temperature change is for a known mass of liquid water, say 1 kilogram of water. And the gradient for this graph is 1 over the mass of the sample multiplied by its specific heat capacity, which for water, I think is 1,886 joules per kilogram per degree Celsius. But you'll notice here that this straight line terminates at some point. So we can extend this straight line down to 0 degrees Celsius and extend it up to 100 degrees Celsius. Now this equation, this linear relationship here, only applies to substances that do not change their phase during this heating or cooling process. So what happens to the temperature during a phase change? So in other words, for example with our water, when we're transferring heat to ice as it's melting into liquid water, well, even though heat energy is being absorbed by the melting ice at 0 degrees Celsius, the temperature of the ice remains constant. So our gradient here is 0. At temperatures below the substance's freezing point, we have a solid. And our specific heat capacity equation applies. But here, we've got a phase change. So we can't use this equation when the ice is melting, or when the solid is melting. And the same is true when we add enough heat energy to our substance to initiate the second phase change, when our liquid is turning into a gas. And when it's in its gas state, the specific heat equation applies again, and we get a linear relationship. So the whole point of this lesson is to show you what's actually happening on the molecular scale during these phase changes, and how we can determine how much heat a particular substance requires to change its phase. So in other words, what is this distance here? What is this change in heat when this substance is transitioning from a liquid to a gas, or from a gas to a liquid? And what's this change in heat when we're transitioning the substance from a solid to a liquid, or a liquid to a solid? So these two values here, these two changes in heat, are going to be different. If we had solid ice and we're giving it heat energy in order to turn it into a liquid, it takes less heat energy to change ice into a liquid than it does to change liquid water into a gas. So what's happening during these phase changes? So this heat energy is being used to increase the potential energy of the molecules in the substance. But none of this heat energy is going into changing the average translational kinetic energy of the molecules of the substance. And that's why the temperature doesn't increase. But the potential energy of the substance during this time does in fact increase. Now this potential energy is present because molecules experience attractive intermolecular forces, and these are forces that act between molecules. So for example, if this is water, where we have one oxygen atom at the top here and two hydrogen atoms, the hydrogen atoms, the water molecules, will experience hydrogen bonding between the oxygen of this molecule, for example, and the hydrogen atom from this water molecule. And we've got another hydrogen bond here, for example, with another oxygen atom. And this occurs throughout the substance. But these hydrogen bonds are attractive. So in order to separate these water molecules from one another, we can add in heat energy to the substance. And what this does is it increases the potential energy of these water molecules, allowing them to move further and further apart, which means that these attractive forces will have less influence over the water molecules themselves. So we're increasing the potential energy during a phase change, but we're not increasing the average velocity of these water molecules. So their velocity vectors, on average, when we sum up all these velocities, will have the same value during the phase change. Outside the phase change, we're both increasing the potential energy and the average translational kinetic energy. When we remove heat energy from the system, the potential energy of these molecules reduce, and these attractive forces become stronger. So if we're looking at the heat required to change a substance's phase from a solid to a liquid, this will be equal to the mass of our sample multiplied by something called the latent heat of fusion. So this distance here for any substance is equal to the mass of the substance multiplied by the latent heat of fusion. And this works both ways. So this works for melting the substance and freezing the substance. So for melting the substance, we're going to have a positive change in heat. And when we're freezing, we're going this way, which means that we're taking away heat from the system. So it would be negative Q value. So this latent heat of fusion is a constant value, and it's unique to each substance. And it can only be found experimentally, much like the specific heat capacity. So this equation will tell us how much energy we need to add to a substance, whatever that substance is, of a certain mass to completely melt it during its phase change. But conversely, it also tells us how much heat energy is released by a substance during the freezing process. So for example, liquid water, when it freezes, it will release energy back out into the environment. And that's because its molecules or particles are giving up potential energy during this phase change. So we know the amount of energy required for a phase change from solid to liquid, but how about from liquid to gas? The amount of energy to transform a liquid to a gas is normally higher than the amount of energy to transform from a solid to a liquid. So the heat energy required to turn a liquid into a gas is again equal to the sample's mass, but is now multiplied by the latent heat of vaporization. And the latent heat of vaporization again can only be determined through experimentation. So if we have a look at two substances, for example water and lead, notice for both substances that their latent heat of fusion, so the energy required for a phase transition from solid to liquid for 1 kilogram, is lower than for the energy required for a phase change from liquid to gas. To transition ice to liquid during its melting point, we need over 300,000 joules of energy, heat energy, per kilogram before the water will start to raise its temperature. But lead requires less heat energy for this phase transition.